Have you ever wondered about the unseen mysteries that govern our universe? This question might sound like a riddle, but it's the foundation of a profound revelation that has reshaped our understanding of the cosmos. We're about to embark on a cosmic journey, exploring the enigmatic entities known as dark matter and dark energy. These elusive components, while invisible to our eyes and conventional detection methods, constitute the majority of the universe's mass energy content. That's right, most of the universe is made up of things we can't see. It's as if we're iceberging through the cosmos, with the majority of its substance hidden beneath the surface of our perception. But just because we can't see it doesn't mean it's not there, or that it's not important. In fact, it's these unseen elements that play a vital role in shaping the structure and evolution of the universe. So what are these unseen entities? Dark matter, the first of the two, is a hypothetical form of matter. It doesn't emit, absorb, or reflect light, making it extremely hard to detect. Yet, its existence is inferred from its gravitational effects on visible matter, radiation, and the structure of the universe. The other unseen component is dark energy. This mysterious force is believed to be the reason behind the accelerating expansion of the universe. It's like a hidden engine, driving the universe to expand at an increasingly faster rate. These two components, dark matter and dark energy, despite their elusive nature, are not just theoretical curiosities. They're the very pillars that hold up our current understanding of the universe. They are the unseen engines driving the cosmos, shaping galaxies, and governing the fate of the universe. Even though we're still in the early stages of understanding these unseen entities, their existence challenges us to rethink our understanding of the cosmos. They push the boundaries of our knowledge and open up new avenues of inquiry. As we venture further into the cosmos, the unseen becomes the key to understanding the universe. Why do we need the concept of dark matter? Let's dive into the intricacies of our cosmos to answer this question. Imagine looking at a spinning carousel. The faster it rotates, the stronger the force you would need to hang on, or else you would be flung outwards. Now, apply this scenario to galaxies. The stars on the outskirts of a galaxy are like those on the edge of the carousel. They're moving at high speeds, and according to the laws of physics as we understand them, they should fly off into the cosmos. But they don't. They stay within the galaxy. The gravitational pull of all the stars, gas, dust, and everything else we can see in the galaxy just isn't enough to account for this. The stars spin around the galaxy as if there's a lot more gravity holding them in place. So what's the missing piece of this cosmic puzzle? Enter the concept of dark matter. This mysterious substance, unseen and undetected in the conventional sense, appears to exert a gravitational pull that keeps everything from flying apart. It's like an invisible cosmic glue holding galaxies together. And it's not just individual galaxies that present this conundrum. Even when we gaze at clusters of galaxies, the largest structures in the universe that are held together by gravity, we encounter a similar problem. These clusters contain far more mass than we can account for, just by adding up all the visible matter. The galaxies within these clusters are moving so rapidly that without the extra gravity provided by dark matter, the clusters would disintegrate. These anomalies, these discrepancies between what we observe and what our current understanding of gravity predicts, suggest the presence of something we can't see, something we can't detect through conventional means. This unseen, gravitationally dominant component is what we call dark matter. Dark matter, then, seems to be a key player in the cosmic theater, silently shaping the universe while remaining hidden from our view. It's a concept born out of necessity, a solution to the gravitational anomalies that defy explanation. The shadows of the universe, dark matter, seem to hold the answers to these cosmic mysteries. But how do we know dark matter exists if we can't see it? Here's the thing, we can't see it, but we can observe its effects. For instance, when we look at galactic rotation curves, we see that the speeds at which stars and gas clouds rotate within galaxies stay constant, even at large distances from the galactic center. This defies Newtonian dynamics, which would expect these velocities to drop off. Then there's gravitational lensing. This is when the light from distant galaxies and clusters is bent by the gravitational effects of intervening matter, revealing unseen mass concentrations. This has given us some of the most direct evidence of dark matter. We also have cosmic microwave background anisotropies. The temperature fluctuations in this ancient light have provided strong evidence for dark matter's existence, showing it played a crucial role in the formation of large-scale structures. And finally, computer simulations of galaxy formation need to include dark matter to match the structures we observe in the universe. Despite its elusive nature, the evidence for dark matter continues to mount. So, what could dark matter be made of? The answer to that question is still shrouded in mystery, but there are a few leading candidates. One possibility is that dark matter is composed of weakly interacting massive particles, or WIMPs. These hypothetical particles are elusive because they only interact through the weak nuclear force and gravity, making them incredibly difficult to detect. Another candidate is the axion, a proposed light, neutral particle that could have been produced in the early universe. If axions exist, they could be floating around us right now, undetected and undisturbed. There are also theories that challenge the very need for dark matter. Modified gravity theories suggest that our understanding of gravity might be wrong, and if we tweak the laws of gravity, we might not need dark matter to explain the universe's behavior. Ongoing experiments and observations, from direct detection experiments to cosmic ray observations, are all part of the global effort to shed light on this cosmic conundrum. The quest to unveil the nature of dark matter remains one of the greatest challenges in cosmology. What if I told you that our universe is not just expanding, but accelerating? Quite the mind bender, isn't it? Yet, this is precisely the extraordinary revelation that emerged in the late 1990s. When scientists were studying distant supernovae, they stumbled upon a cosmic conundrum. The expansion of the universe wasn't slowing down due to gravitational attraction, as one might intuitively expect. Instead, it was speeding up. This counterintuitive observation threw a galactic curveball at our understanding of the cosmos. It suggested that there was some unseen, mysterious force at play. A force so powerful, it was overriding the gravitational pull of all the matter in the universe. This strange repulsive force was given a name: dark energy. Now imagine a balloon with tiny dots all over its surface. As you blow up the balloon, the dots move away from each other. Similarly, galaxies in our universe are moving away from each other, not because they are traveling through space, but because space itself is expanding. And it's not just expanding, it's doing so at an ever-increasing rate. Dark energy is thought to be the culprit behind this cosmic acceleration. It's like an invisible, repulsive force that's causing space itself to expand faster and faster. It's a bit like anti-gravity, a force that works in the opposite direction, pushing things apart rather than pulling them together. But here's the kicker. Dark energy is not just a minor player in the cosmic game. It's estimated that it makes up about 70% of the universe's total energy. That's right. This mysterious, unseen force that we're still trying to understand is the dominant entity in our universe. Yet, despite its cosmic dominance, we know very little about what dark energy is or how it works. It's one of the most significant unknowns in our current understanding of the universe. In a twist of cosmic irony, the force driving the universe apart remains one of its greatest mysteries. It's a cosmic riddle that scientists are still working hard to decipher. The accelerating universe and the enigmatic dark energy serve as humbling reminders of how much we still have to learn about our vast, mesmerizing cosmos. And how do we know about this mysterious dark energy? You might ask. Well, our understanding is largely based on two key pieces of evidence: supernova observations and measurements of the cosmic microwave background radiation, or CMB for short. Let's start with supernovae. These celestial explosions are not only spectacular to observe, they're also incredibly useful for cosmologists. You see, there's a specific type of supernova known as type Ia, which has a consistent maximum brightness. This makes them what we call standard candles, objects that we can use to measure astronomical distances. Observations of these type Ia supernovae have revealed something astounding. The expansion of the universe is not slowing down, as one might intuitively expect from gravitational forces. Instead, it's accelerating. This unexpected acceleration was a game changer. implying the existence of a mysterious, repulsive force. This force, which seems to counteract gravity on the largest scales, was given a name: dark energy. And while it might sound like something out of a science fiction novel, it's estimated to make up around 70% of the total energy content of our universe. Now, on to the cosmic microwave background radiation. This is the afterglow of the Big Bang, and it's been traveling through space for over 13 billion years before it reaches our detectors. Detailed measurements of the CMB have allowed cosmologists to map out the early universe and make precise calculations about its composition. These calculations strongly favor a universe dominated by dark energy. So there you have it. From the exploding stars millions of light years away to the faint echoes of the birth of the universe, we find the fingerprints of dark energy. It's a puzzle that's far from solved, but piece by piece, we're building up a picture of our complex and mysterious universe. Just as with dark matter, the evidence for dark energy is hidden in the light of the cosmos.